All right. So greetings from India. I am Dev Samriddhi Arora, and I'm an assistant professor at University of Allahabad, India. And in this work, I will present a brief and crisp review of geological evolution and sub-ice geological framework of Princess Elizabeth Land sector of East Antarctica. We know East Antarctic Shield holds a unique archive of the past and preserves remnants of almost all supercontinents, obviously archived in form of orogenic belts. It is imperative to have profound knowledge of the sub-ice geology to understand its effect on the overlying ice sheet. So starting with Princess Elizabeth Land, So starting with Princess Elizabeth Land, it is one of the least explored sectors of East Antarctica, both in terms of the sub-ice geology, as well as regional glaciological and thermotectonic history, especially in the interior sectors. PEL is a crucial component of Gondwana assembly. Boger et al. Divided Antarctica into 4 main categories on the basis of their affinities with the correlatives within Gondwana. So you can see in this figure, the coastal sector has Indian affinity, whereas the interior has no affinity as per today's data. PEL also holds the Lambert Graben, which has been reported to be conjugate with the Indian Mahanadi Graben of India. The Lambert Graben hosts world's largest glacier, the Lambert Glacier, and one of the largest drainage system present here, associated with the Mayuri Ice Sheet, which with reported very strong flow convergence and acceleration near the coast. As seen in this left figure, most of the exposed part of PEL, exposed outcrops, have been considered a continuation of Rainer terrain, essentially, which is reported to be primarily of Meso to Neoproterozoic in age. So in this work, I will present evidence that this sector has much more complex geology than what has been explained previously. Okay, so beginning with a wider view, the sparse data set that existed for depiction of topography of PEL had the last remaining front of Antarctica, as seen in this right figure. This large data gap is recently filled by IceCap2 data. It revealed previously unmapped highlands and lowlands present beneath the ice cover, shown in this center image. Also, the new radar data also confirmed presence of an assortment of previously reported by Jamieson itself, previously identified subglacial lakes and complex subglacial geomorphology. So this IceCap data also confirmed that the presence of a 1,100 kilometer long system of canyons and 2 large lakes connecting inland sector near the tail of Lambert to the coast. Fortunately, I was part of this work as a student participant. This work also contributed to geophysical data which was missing in the area. So to understand the bedrock geology, aeromagnetic data is extremely useful. I mean, we get a synoptic view of geology of bedrock from aeromagnetic data. The high resolution aeromagnetic data from IceCap2 interpreted the Indo-Australo-Antarctic suture, along which the collision between India, Antarctica, and Australia happened during the final amalgamation of East Gondwana. However, the anomalies present in this area or in PEL are needed to be correlated with the rock record to understand the complex picture and the complex geological framework of this area. I will explain the importance of this map in the later slide as well. Now let's see the geology of the exposures. So the coastal outcrops of PEL are classified into 3 broad categories. One is Archean aged westfold. The second one is Archean to Paleoproterozoic aged raw group, and a large section of coastal as well as inland fringe of PEL is regarded as a continuation of the Rainer terrain. For almost a decade, there has been ambiguity regarding the major metamorphic or orogenic event of this sector. It was earlier proposed to be a granular event about 1100 MA and later on contemplated as a Pan-African belt of 500 MA. However, the geological events in the time frame from 1000 to 500 MA still remains cryptic, though there are some data present, and I will show it in further slides. So I investigated granulates of this terrain. Two granulate grade events are recorded in this terrain at 800 and 500. PT estimations and pseudo-section modeling show a clockwise path. Just a second. A clockwise path showing a relic high pressure granulite grade event, followed by decompression and reaching ultra high temperature conditions. This is the peak temperature. Texturally constrained monazites record no granulation event at all. 800 MA event is typically recorded in monazites present as inclusions within garnets. And the decompression of about 5 kilobar is indicated, suggesting a tectonic uplift of about 15 kilometers during the closure of this orogeny, this Pan-African orogeny, which again signifies that at that time also thrust-related tectonics similar to the modern tectonic, modern orogenic belts exist. So interestingly, same frame of ages have been confirmed by texturally constrained monazites as well as zircons. So chemical dating of monazites and the time ages extracted from them indicates these monazites and zircons are from peletic granulites. So these indicates 4 isochron ages, as you can see in this figure. The ages are 498, 649, 766, and 906. Similarly, 830 is extracted from core of zoned monazite grains, and 501 is extracted from rims of zoned monazites and the unzoned monazites present in the matrix. It's actually interesting as well as lucky to see that zircons also record these events, concordant ages of 519, 718, 783, and an older component of 1070 MA are recorded. So this confirms that this terrain is not simply Grenvillian or Pan-African. It has a continued history from Rodinia amalgamation to Gondwana amalgamation, and we still have very little idea what happened in between. So by correlating this much data of Larsemann Hill area, which is present here, with the Chilka Lake and Rengali domain, these domains are present in eastern India. Obviously, Rainer terrain has already been correlated very well with EGMB, which is Eastern Ghat Mobile Belt of India. However, this area had not been correlated directly prior to this paper. So by correlating the granulites of Larsemann Hills with Chilka Lake and Rengali domain, and by comparing their published geochronological data, I speculated 2 remnant orogenic belts passing through PEL and conjugate Indian sectors, suggesting that the Pan-African belt can be speculated as a branch of the IAS proposed by the aeromagnetic data. And also it can be speculated as the continuation. It actually follows the same trend as proposed earlier by other workers. It follows the continuation of the Tunga suture. This Pan-African suture is also confirmed by structural data compilation, Gupta et al. 2021, proposing a suture which connects the Rengali domain of India to Roar, which exists at the coastal fringe, to Rukar. Rukar exists at the southern Prince Charles Mountains. I mean south sector of Rainer complex. So, because this area has the long system of cannons, 1100 kilometer long system of cannons, To understand the relationship of those canyons to the Lambert Rift, the structural analog modeling was done. It was noted that the canyons flow a trend parallel to a foliation trend seen in the field, also marking the post-oblique trend of the Kunga suture, as I discussed in the previous slide, also supported by the post-oblique magnetic anomaly, as you can see in this section of EDMAP. The idea was to understand if the canyons follow a predefined rift, providing so like a failed rift probably, which is providing higher heat flux to melt the ice. So the experimental result in case of extension direction orthogonal to the zone margin provided favorable results. As you can see, there were two anisotropies marked. One is parallel to the zone margin and one is at 45 degrees, as you can see simulating this setup. So parallel anisotropy gave the parallel anisotropy gave rise to a well-developed rifting, simulating the Lambert graben. And the angular anisotropy, as you can see here, which is at 45 degrees to the Lambert one, gave a segmented rift faulting. So this kind of showed the nature of the canyons, what we are getting here. Keeping in mind its connection to the Lambert graben, the rift beneath the canyon system is also speculated to be a failed graben, which opened up prior to Gondwana rifting. So this was about PEL, a very short and crisp review. Here I briefly compare the PT evolution paths of three terrains. Now, if you want to see a bigger picture, it has to be compared on a regional scale. So three terrains is one is coastal PEL, second is inland PEL and including Grove Mountains, and third one is Rainer terrain. As one can see, all these three terrains registered ultra high temperature metamorphism. Larsemann and inland sector of PEL shows a typical clockwise PT path, whereas the Rainer terrain is typically considered to have involved an anti-clockwise PT evolution dominated by isobaric cooling. UST signatures with a clockwise path in coastal and inland PL probably indicates continent-continent collisional scenarios and hot underplating of the asthenospheric mantle at the crustal depths when we are talking about the Indo-Antarctic amalgamation during Gondwana. Whereas the UST anti-clockwise paths here of Rainer indicate elevated geothermal heat flow. It seems Rainer has a different geodynamic history, and it is still a puzzle whether it is a separate terrain or not, because we do find similar age signatures. So so this 800 event is always called enigmatic or has been ignored as a resetting event of Grenvillian. But as I showed in earlier slide also, where we used multiple chronometers, as well as here, I made a simple plot using showing the frequency of ages reported in Larsemann Hills, and you can see the 800 ages are much higher than the Grenvillian ages reported, similar to the Pan-African ages. Pan-African age is the youngest event, so obviously we will have more signature of it.
We have 1 minute left, okay?
Sure. This is just last time. So similar ages, 800 concordant ages are reported from other sections, let it be Grove or Rainer terrain. I find it intriguing why these ages are always referred to as enigmatic or simply ignored, despite being concordant like 1000 and 500 mm. I believe backed up by the data, there are multiple cross-cutting orogenic belts present in the Rainer PEL terrain. These fabric-defining orogenic belts are crucial to understand not only the amalgamation and breakup of supercontinents, but also the responses of crust and heat from Earth's interior on the overlying ice sheet. So this short review is a part of GeoEAIS project, which is an India-led program started last year itself. to explore the inland regions of PL. Hopefully, we will have a better picture of PL, especially the inland regions, after investigating the untouched exposures and correlating their geology with the geophysical data. Thank you.
Thank you very much. Unfortunately, we don't have time for questions, but there are a couple of questions in the Q&A. So Deb, if you've got time, you could maybe type some answers into the Q&A. And if we have time at the end of the session, we can come back to some discussion on that. So our next talk, is that okay? Thanks very much. Our next speaker is Lu Li, who's going to talk to us about Antarctic lithosphere density and heterogeneity and insights for solid earth and cryosphere interactions. So over to you. Thanks.
Yeah, can you see my screen?
We can, yes, thanks.
Yeah, cool, thank you. Hello everyone, my name is Lu Li. I'm a PhD student at the University of Western Australia. And today I will show you some work about modeling the lithosphere density structures, and also what we can learn in terms of understanding the cryosphere and solid earth interaction process. So here just brief illustration about we got different structures from the basal ice sheet. We got sedimentary basins and can provide water and sediments. We also have crust with different density and thickness can conduct heat and also generate heat by the heat productions in here. We also have, the lithosphere and sensosphere have different temperature. So the density structure is great. They can tell us a lot of things about tectonics and about exhaustivity. But I think in terms of understanding the ice sheet, we need to understand the thermal mechanical structures. So in this talk, I'll be focused on to use the gravity inversion to estimate density structures and combine the other information to estimate the temperature in the Antarctica lithosphere mantle. So the work is for the crust part of the crust part of the model is based on my previous modeling work. So if you're interested in that part, you can scan the QR code in here. So we got a crust structure from my previous model, and we convert the seismic tomography model based on Andrea Loy's work to an initial temperature and density within solve the density structure. So basically, the seismic velocity is sensitive to both compositional change and also the temperature change. So if we know the seismic velocity, we know one of each of the three and no parameter, we can uniquely constrain the residue. So the idea is we assume an initial composition of the Antarctica lithosphere. We convert the seismic velocity to an initial density and temperature. So because gravity is sensitive to the density change, we then can use gravity as a constraint to correct the density distribution. Then use this updated density with the tomography model, we can get a consistent composition and the temperature structure in Antarctica. So that will answer the first goal of this study to understand the thermal mechanical structure of Antarctica lithosphere. So based on the temperature, we can estimate the mantle viscosity and the geothermal heat flow. And the other interesting question is when we cooperate the compositional change, so what the capacity of the composition in understand the thermal mechanical structure, and also if there are any other unknown uncertainties we need to cooperate to better constrain the structures. So once we get the initial density distribution, we then use a software called, it's an open source software called Descript. So we got a new software can solve the gravity with unstructured mesh in the geodetic coordinates. So it can also parallel run in the supercomputer. So it's very handy. So we can, solve the density distribution in the lithosphere in one go. So I just show you some step slides about the inversion result. So we correct the densities and estimate the temperature and the composition. So you can see the predominantly difference. We got very hot and thin lithosphere in West Antarctica, and very low and dense and highly depleted cratonic lithosphere in East Antarctica. One thing I want to see is the dashed line is the initial 1200 degree altitude is our initial estimation about the lithosphere thickness. Once we incorporate the compositional change, we see there are roughly about 10 to 50 kilometers higher temperature. So 10 to 50 kilometers difference in terms of the new lithosphere thickness. We got this the depth slides about the temperature distribution. Then we convert the temperature to the Mandel viscosity. So we see there are several low viscosity regions in Amnesty and Bayman or Mary Berland in West Antarctica, and about 200 kilometers, we see there are relatively low viscosity in the downstream region in the Toten area. So that may impact some potential uplift in estimate the GIA in here. We also are using the update temperature field to estimate the lithosphere thickness. As quite surprisingly, there the central East Antarctica and part of downstream side of the recovery region have really thick lithosphere, about like 350 kilometers. And we using the updated crust temperature as a boundary condition to generate a new heat flow maps. The West Antarctica is quite high for the heat flow parameters. I will talk about later. This higher heat flow are mainly due to the attenuation model we choose. And we also see the coast region in East Antarctica have higher heat flow, and also some center of the East Antarctica have relatively high heat flow. So that's kind of answer the first part of the question to understand the thermomechanical structure of Antarctica lithosphere. So then we can start to think about what else information we're missing to better constrain this process. So here show just a brief illustration about how we convert the seismic velocity to temperature and density. So basically the seismic velocity are combined by two parts. One is the elastic part in here, and one is the unelastic part associated with the attenuation model. So combine these two, we can get a forward calculation about velocity field. So if we look at the top left part of the figure, so these two lines have basically have the red and red one have different attenuation model but have same composition. These two lines can overlap together. So for the high velocity area, the major difference are dominated by the compositional change. So that's the situation in East Antarctica. We have this very fast seismic velocity. But if we got this low velocity but high temperature area, the temperature difference are dominated by choosing different attenuation model. So it means if we want to understand the thermal structure in West Antarctica, we need to better estimate the thermomechanical the attenuation model to understand this low velocity area. So at the start of this year, there's a kind of great paper they're using some Bayesian approach to calibrate these inelastic parameters. I think one way to move forward is to both we calibrate this inelastic parameter and with the compositional impact in here, so that we can better constrain the thermomechanical structure in Antarctica. So in short summary, we generate a new thermomechanical model in Antarctica. Based on this, we estimate the Mandel viscosity and the geothermal heat flow, and also incorporate the composition. We can lead to about 100 to 150 degrees hotter mantle in the highly depleted region. That can roughly give us about 6 to 10 milliwatt per meter a square higher heat flow. And also we can expect there be about 10 to 50 kilometers change about the thermal lithosphere thickness. And the inelastic parameter remains quite large uncertainty, especially for the West Antarctic area. If we want to better constrain the thermal properties, we need to consider to calibrate this inelastic parameter. So here's some reference to this work, and I'm happy to take questions. Thank you.
Thank you very much. And yeah, I've realized it's very difficult for us all to clap and say thank you. So thank you very much. Yeah, I have a question here from Terry Wilson. Have you compared your viscosity, lithospheric thickness, heat flow with published results derived from seismic data? And if you have, how different are they?
I didn't compare the viscosity. I compared some part of other model also based on the Andreas Law's tomography. The pattern is quite similar, but I think because we use different attenuation model, there'll be slightly different, about maybe up to 1 magnitude of difference in terms of viscosities. The lithospheric thickness, if we check, there's the preprint I showed you previously, based on the new Angelos model, they also see this very thick lithosphere in the center of East Antarctica. I think it's kind of like tomography related, the thickness. And the heat flow, the pattern is quite, I didn't compare the individual measurement, but I do see there's kind of similar pattern, but the amplitude is kind of slightly different from my model.
Thanks. We have time for one final little question if anyone wants to type in the chat. But if you can unshare your screen, Luli, that'd be great. Thanks.
Oh yeah, sorry. Sorry.
So I don't see any other questions just now, so we'll move on. But thank you very much. It'd be interesting actually to discuss how all these, both the previous talks, how this sort of data might influence things like basal melting and ice flow as well, if we want to sort of think about the sort of the importance of this down the line.
Sorry, how do I?
So
okay, stop sharing.
That's it. Perfect. Super. Okay, so thank you very much. Our next speaker is Maximilian Lowe, and he's going to be talking about more on heat flow and elevated heat flow beneath the northern transantarctic mountains using spectral analyses. So Max, I'll hand over to you. Thank you very much.
Thank you.
If you can go on. Yeah, we can see that as well. That's great.
Okay, perfect. So I want to talk about hot mountains in Antarctica, more precise. Want to talk about geothermal heat flux in the area of the Transantarctic Mountains and the subglacial basins. So what is actually geothermal heat flux? Geothermal heat flux describes the transport of heat from the interior of the Earth to the surface, and it is important in the context of Antarctica because it can influence the rheology of the ice and also can lead to basal melting, which then can enhance the flow of the ice. And we want to understand better the behavior of the ice sheet in the future, especially in regards to runoff in the oceans and global sea level rise. We need to better understand the contribution from the solid Earth to the stability of the ice sheet. So, but geothermal heat flux can tell us also a lot about the tectono evolution of Antarctica. So it's a very important parameter to understand Antarctica better. But unfortunately, as the figure illustrates, we have only little direct measurements in Antarctica, a few offshore, but onshore only really little. And that's due because the the rocks are hidden beneath a thick ice sheet and are not exposed at the surface, and we have only a few drilling programs so far. So what can we do if we cannot measure geothermal heat flux directly? We can use geophysics to infer geothermal heat flux, and recent geothermal heat flux models have used magnetic, gravity, and seismological data. All these continent-wide estimations agree quite well on the continental scale that they see that East Antarctica is much colder than West Antarctica, but those models differ quite remarkably on local scales, which this figure illustrates. So we are far from having solved geothermal heat flux for Antarctica so far. One reason where the difference come from is obviously the difference in methodology, but also every model deals with sparse geophysical data coverage, and also some of those models use quite large grid cells because they calculate geothermal heat flux for the whole continent. So we wanted to do a different approach where we not try to estimate geothermal heat flux for the whole continent, but rather pick a local area and try to improve geothermal heat flux estimates for a local study area, which in this case is Transantarctic mountains and subglacial basins. And we use magnetic data to do that, similar to the Martos approach with a few variation the method. So how does it actually work? How can we use magnetic data to estimate heat flow? Basically, we are searching for the bottom of the magnetic layer, which is called the Curie depth point, which correlates to the depth at which magnetic rocks lose the ability to generate a magnetic field due to an increased temperature. And that temperature is the 580 degrees isotherm called the Curie temperature. And how we do that is we have our magnetic data here, only airborne data, and we use a moving window approach where we calculate for every window the power spectrum of the magnetic data, and from get the pointer here, and from the power spectrum we can calculate up and the centroid of the magnetic layer in a different part of the spectrum. So the top of the magnetic layer would be the medium part of the spectrum, and the centroid calculated on the low wave number part. One difference to the Martos approach we're taking here is that we only use airborne data. So we can see that we have some areas with really good coverage, then areas where we have only a few flight lines. So we're dealing with large data gaps in the data. Previous studies have merged the airborne data with satellite data, overcome the problem, but that overlooks an important factor, that the chosen window size is also a low pass filter. It means if you have a 200 by 200 window, you cannot have wavelengths that are longer than 200 kilometers. But the magnetic satellite models, for example, MF7, they have only wavelengths larger than 300 kilometers. So you're merging something into your data which isn't giving you meaningful information. So we don't use any satellite data. We deal with the data gaps by interpolating the data in the window, and in the next step we calculate how much real data we actually have in the window, and we do a cutoff. So we throw the results from windows with less than 80% data coverage, we throw them out, which means we are limited to areas where we have really good and dense airborne data coverage. If we go to the results now, we can see already the fact that we removed large parts where we have only few flight lines. And what we can also see is that we have higher higher resolution in this pattern of our Curie depth than the Matos model. That's due to the step size of our window. So we use 20-kilometer step size. So we have a Curie depth estimation every 20 kilometer, while Matos for whole Antarctica used 175-kilometer step size. So that's already the higher resolution comes from working on a local area, having more estimations. The other thing that we can already see is that the using window size already influenced the depth of the Curie temperature. With increasing window sizes from 200 to 400 kilometer, the Curie depth increases, but the overall pattern stays the same, basically. So from the Curie interface now, we can forward calculate geothermal heat flux using constant thermal conductivity for the crust. So that's basically a linear transformation of the Curie depth to geothermal heat flux with already strong assumptions that we have a homogeneous crust. But regardless, that's our results. And what we see is that beneath the Transantarctic mountains, we have much higher geothermal heat flux, which is really interesting. But also we have linear features in the Rennigraben, in the Liljegraben, and in the central basin of the subglacial basins here. Yeah, that's actually interesting because previous seismological studies have found that with receiver functions, the Hansen et al. 2016 study over the Transantarctic mountains, that the Transantarctic mountains have 10-kilometer, too little crustal roots to be isostatic balanced, and they explain that the mountains are still there because they have thermal support from hotter and less denser mantle material. And also Shen et al. Study found low velocity zones beneath the Transantarctic mountains, which they interpreted as hotter mantle material. And so the seismic studies predict that the Transantarctic mountains are thermally supported by less denser and hotter mantle. We find same things with an independent method using magnetic data, that we have a very high heat flow beneath the mountains, which would be aligned with the idea of thermal support for the mountains. Additionally, we see our heat flow patterns are in line with recent volcanoes, or still active volcanoes, marked by the yellow stars, which is a nice ground truth that this method works, because we would expect high heat flow in areas where we have active volcanoes. However, we come to the conclusion that the heat flow beneath the Transantarctic mountain are consistent with recent active volcanoes, shallow Curie depth, and high geothermal heat flux estimates beneath the Transantarctic mountains provide independent support for the hypothesis that we have warmer West Antarctic mantle beneath the Transantarctic mountains. And yeah, spectral analysis of magnetic data can give a robust estimation of relative variation in Curie depth, and therefore relative geothermal heat flux estimates. But I didn't have time to talk about the uncertainties, but with that method, there are huge uncertainties involved, and taking absolute geothermal heat flux estimates based on spectral analysis of magnetic data should be used with caution in other models, basically. So it gives you a good indication where you have areas of warmer material and areas of colder, but putting on a number that's how much it is need to be dealt with caution. And one major point I want to make here is that if you use spectral analysis of magnetic data to estimate the Curie depths, you need to be very cautious with the wavelengths you use, and using satellite data might not be the best idea. Of course, you're limited then to areas where we have a lot of airborne data, which is not the case for the whole Antarctica, but yeah, we would suggest to use this method only in areas where we have high airborne data. With that, I thank you. Please get in contact if you have any questions. If I'm officially back from holidays next week, I plan to submit in paper to JGR, Solid Earth, including those results. And in that paper, we discuss more of the uncertainties, and we also compare our results to recent geothermal heat flow models. Yeah. And with that, I thank you again, and I'm putting here some faces to the names of the co-authors. Yeah, thank you.
Thank you, Maximilian. We have a question on the Q&A from Leonardo, which is, if the windows are 200 kilometers in size, then how realistic is your isotherm depth estimation, since it's quite deep and would therefore generate a very long wavelength anomalies? So how confident are you that the depth you estimate really is the Curie depth?
Yes, so the discussion which window size should be used is quite an important one, and different authors suggest different within different window sizes. We followed the Rawat 2007 recommendation that the window size should be at least 5 to 10 times the recovered depth. So if we have 30 kilometer Curie depth, we would expect to have a window size of 300 kilometer. So that's why we tested 200 to 400, because we expected to have our Curie depths between 20 to 40 kilometers. Yeah, I'm not sure if that answered your question, but
I don't know either. But Leonardo, you can continue the discussion in the Q&A. Thanks.
Yeah, for that. I mean, just to add to that, of course, the Curie depth point is just 1 point for one window, and you average throughout the 200 by 200 window size or 300 by 300 window size. And of course, if you have a lot of variation in Curie depth in that area, then that will bias your average depth, basically. Yeah.
Thank you. Super. So we'll move on now. And our next speaker is Peter Fretwell with the shortest talk title of the session, and that's on BedMap 3. If you're able to share screen, Peter, thanks very much.
Thank you, Stuart. Just let me put it in presentation mode. Okay, is that okay?
It is, thank you.
Excellent. So this is going to be a short talk about our BedMap 3 projects. I would imagine most of you will be aware of the BedMap projects, but as a quick overview, introduction, this is the third iteration of BedMap. The first, which is the map of the topography, the bed topography underneath the ice in Antarctica. I'm going to also start with an apology that anybody who went to the Rings conference, you'll see a very, very similar talk today to the Rings conference a few weeks ago. And also, just a quick plug, there's another talk more on the data side of this, a little more diving into data on Thursday, I think, at the data session. So anyway, a quick introduction. BedMap. This again is the third iteration of BedMap. First one is published in 2000, the second in 2013. So we're almost 10 years now since BedMap 2. Since then, of course, there's been BedMachine, very successful, which was a hybrid model incorporating excuse me, modeling around the coast, but it incorporated new data as well from Mathieu and many other collaborators. The BedMap 3 will be very similar in its scope to BedMap 2. So our remit really is a SCAR group to produce an updated version of BedMap using all the community data we could find, but also critically, we want the community wanted to make all of that data standardized and available to all of the modeling community, well, to all of the community really. So a big part of BedMap 3 isn't just making the grids, it's also standardizing the data and making it available in a seamless way to the community. So this will include over the next year a couple of different publications, one on the data itself, and the second one will be on the grids. First paper, we're just about to submit it, we're just about to send it out to all of the co-authors, which is a large list because it includes all of the data providers. So there's almost 100 co-authors, I think, on that list. And the second will be the gridded products, which will probably come either later this year or early next year. But I'll talk a little bit about timelines in a short while. One of the key parts of providing the data is that it's all going to be standardized. So if you get data now from different organizations, it all comes in very, very different formats with different attributes, different things are recorded using a lot of different nomenclatures. We've taken all of the data from the last 60 years of radio echo sounding and seismic data. So it's mostly those sorts of geophysical data that we're using. And we've standardized it all into a set format using the FAIR data standard that's findable, accessible, interoperable, and reusable. And we've done this for both the old data from BedMap 1 and BedMap 2, but also the BedMap 3 data as well. And here's the coverage that we got from those 60 years of geophysical data, with some figures by the side. So campaigns, BedMap 1, 127. So the campaigns in BedMap 1 were voluminous, but the amount of data, actually amount of point data measurements, wasn't that great. Because if you think all of those radio echograms, they've got point measurements, and that's what we're using, just for the bed in this case. BedMap 2, 25 million points, but BedMap 3, we've actually had 50 million points in the last 10 years. And you can see here, this yellow is BedMap 1, green BedMap 2, purple BedMap 3, and the combined there is the whole thing. So you can see we've had a lot of new data, including a lot of archival historic Russian data, all of the Princess Elizabeth Land data, and the ice cap data, as well as stuff over Concordia, the oldest ice projects in East Antarctica. So if we're talking East Antarctica, they're probably the bits that you're interested in. So there's volumes of data. So this data has all been standardized, and it's going to be made publicly available over the next few months. And here's an example of what you're going to get. The data comes as two different types. There are the original data that's been provided for us, and we're setting it out in CSV files, which are an ISO data standard with all of the metadata included, with all the things you might want to include, like correct word failing corrections and velocity data and things like DOIs and who owns it, as well as all of the actual attribute data there as well. If we haven't got any information there, it's given a null value. So there's quite a lot of null values in there as well. But as well as the actual raw underlying data, of which there are 76 million points, we've also taken each 500-meter grid cell in the BedMap, and we've worked out the statistics of the data in each 500-meter grid cell. And we're giving that out as shapefile points. So for instance, here's what you would get in that shapefile. You would get all the statistics from a particular campaign of that 500-meter grid cell. So it's not all of the data, it's just from that particular campaign. And it gives you all of this data here. And that means that we can work out lots and lots of different useful things about bed roughness and variance in the data from each different campaign, and also use that to look at crossover errors and things like that with those 500-meter grid cells. So the way we're going to disseminate this is from a web portal. It's basically the same web portal as we use for the Antarctic Digital Database, another SCAR product, if you're aware of that. And here you can see this is the whole data. It's not quite the right color scheme. We're probably working on the color scheme, but it will be very similar to this. There's a download, and you'll be able to download either the shape files or the underlying CSV files, and also eventually all the gridded data as well. So that will be the web portal, which will be coming out in the next few months. The data download itself, it's based on a Ramada system, and you'll be able to get each campaign individually or the whole data set for each of the 3 bed map campaigns. And it comes through a SCAR, it's a SCAR project. It comes through a SCAR web address. Each different data set will have its own DOI, both the underlying data, but also the actual full data sets as well. So each DOI will have three different entities, both for the shape files and for the CSV files and for the overall data. And the aspiration is to make it all machine readable over the web. So that's the first bit, that's the data paper. The second part is the actual gridding, a new grid of bed. This isn't it. This is a very rough one I put together. We'll obviously incorporate the offshore bathymetry as well, using the new GEBCO, using the new IBSCO 2 that's come out recently. And we're going to concentrate a lot on the fast flowing ice streams and using a lot of the new data there. One of the considerations we have to take into account is what gridding algorithm we use and what detail we grid. So here is an example I've just put together quickly of something gridded at 500 meters square. So I think the last one, that one there, is at probably 2 kilometers. This is if you grid it at 500 meters, and you can see all of the lines come out there. So we're probably going to be making a hierarchical gridding system where we have different resolutions in different places. That gives you an idea of what it's going to look like over East Antarctica. But it won't look quite like that because, as I said, we'll merge in the coarser areas in a more intelligent way. We're also making a new grounding line. So the grounding line, we're taking all of the published satellite data of different grounding lines, and we're making one seamless continuous grounding line from that. So Hamish has been doing this recently, using some of the SAR data and the tidal prism data to make one seamless one, because at the moment there isn't a seamless good grounding line that we can use. So that'll come as part of the bundle of new data sets as well. We also have we think we have a new thickest ice statistic, but I can talk about that later if you want to talk about it. So the timelines, we hope to be submitting the first paper by the end of August 22, if all of the many authors get back to us in time to, they've still got to see it, but we're going to be sending that out to authors over the next week or so. The second paper with the grids will probably be coming autumn or towards Christmas 2022, with publication hopefully by EGU. We'll also be making a new printed map, so you can replace that one on your wall, Stewart, and hopefully that will be given away. We'll have a large distribution of those at EGU in 2023. So that's our plans at the moment. So just a very quick rundown of our plans for BEDMAP 3. Thank you very much.
Thanks, Peter. And I'll expect my new map in the post whenever it's ready. Yeah. Does anyone have any questions? Then please type them in the chat. While anyone is doing that, I guess I have one question, and that is, if you have different uncertainties with different surveys and those are overlapping, how do you deal with that in the gridded product? Are you simply ending up sort of taking a mean, or I mean, how do you deal with the sort of, let's say, the variation in data points that you might have within that pixel point?
It depends upon the data itself. So we know, for instance, the old SPRI data and the old BedMap1 data is quite inaccurate because it's not got GPS associated with it. So in that case, that would be binned and we would use the new data sets. For other data sets, we will use a median probably of whatever's in there, depending upon how many data points are in there, and we will use all of it together and it'll work out what the mean or median is of those data points. So it's very hard to say which is correct, but in some places we can check, and we've been doing this as a sanity check. We can check lines. So if we find that there are crossover errors, we check the lines to make sure that this one isn't crossing over errors further downstream. So as I said, the oldest ice, sorry, the thickest ice, we think is actually at the moment wrong because it's a crossover error of an old data set, and that whole line will be taken out because we can check those crossover errors, and it's quite a manual process, unfortunately, which is why it takes so long to do these things.
Yeah, and I guess I'm going to hog the limelight in terms of data spacing. I mean, you showed those maps of the sort of how closely or how well resolved the spacing is, but in terms of proximity to the grounding line, does it still leave quite a lot of work to do for, I guess, for the rings team? You know, is there still quite a big sort of gaps in between lines near the grounding line?
It's mixed. What we find is that in very crevassed areas, then the radio echo sounding often misses out, doesn't get the bed, it falls out, and therefore we have a lot of problems in particularly crevassed areas, particularly from older surveys that haven't got that haven't been done at the right height or had the right power. So it's quite a mixed picture there. So there are some gaps around the grounding line, especially in some places, for instance, like I'm trying to remember the name of it, Enderby Land, I think it is, and places like that where the data isn't so good. Around West Antarctica, we've been spending a lot of effort around Thwaites and Pine Island and places like that, and the data sets in there are much better. So it is a very mixed picture, but generally for fast flowing ice streams, most of them have been reasonably well covered, but not all. Places like the Cook Ice Shelf, for instance, is devoid of data for much of it. So it is a very much mixed picture.
Thank you very much. Excellent. So I think we'll let you off the hook, and we'll move on to our next speaker, and that is Edmund Lee. Peter, by the way, there's a question on the chat there in terms of the licensing. You might want to type in a response if you can find the time. So yeah, our next speaker is Edmund Lee, and he's going to be talking about mapping subglacial landscapes in central East Antarctica. So over to you, Edmund. You can share screen.
Okay.
Yeah, and just put it on slideshow. Brilliant. Super. Thank you.
Great. Hi everyone. I'm Edmund Lee. I'm here from Durham University today to present some work that I've been doing as part of my master's, studying with Stu and Michael Bentley as my supervisors. Essentially, what we wanted to do is follow up on a principle that has been elucidated in previous research, whereby we can actually see a qualitative relationship between the shape of the ice sheet surface and the large-scale structure of the bed topography. So we can use images like the one on the left here to actually map the plan form geometry of where subglacial valleys and ridges are located. We're taking these principles and applying them to map an area of the Gembutsa subglacial mountains in central East Antarctica. The reasons for choosing this area are a few, but mainly we already have fairly good radar survey data from the AGAP survey, which gives us a a very reasonable impression of what the central area of the Gambertses looks like in terms of the structure of the topography. However, the surrounding area is still actually quite poorly resolved, and that gives us the opportunity to both use the existing radar data as a kind of validation for our new mapping, and also potentially to improve upon it. We know this is an area of high relief and low ice velocity, being sitting beneath the Dome ice divide, which is quite good conditions for producing turbulent ice flow, which is likely to cause the subglacial topography to kind of have a surface expression. Some of the questions we can ask about this landscape in terms of its origins and evolution. These are still kind of relatively open questions. We think it's overall a landscape that has evolved through multiple different phases, and it might be potentially quite old. And another corollary to that is that there may be locations in this area where long-term coal-based ice is preserved, and there's a potential for us to be able to get at that a bit with some of this mapping. So just to briefly go over the data sets we're using here and how we're using them. There are two main data sets we used in the mapping. The first is the reference elevation model of Antarctica, published in 2019, which is a high-resolution digital elevation model created using high-resolution satellite imagery. The purpose of this data then is to actually look at the change in surface slope across the ice sheet in the area that we're interested in. So we can see on this figure, on the left-hand side, the top three panels all show the same profile from the REMA model. The top one is the actual surface elevation. The second one is the surface slope. So that's the first derivative, showing essentially the rate and change of elevation. And the third one then is the second derivative, the curvature, which is the rate and change of slope. And what we can see is that broadly, there is a good qualitative relationship between the position of the greatest slope, and that translates also to a transition from positive to negative curvature, and the position on the bottom panel, which is actually a profile from the AGAP radar image for this profile. There's a good relationship with the position of the actual the peak in the subglacial topography. The second data set we're using is a radar image from the RadarSat Antarctic mapping project, which you can see in panel D, has a good correlation with the surface slope because the intensity of the radar reflection depends on the angle of the surface slope. So if you look at the right-hand side, you can see how we actually use these data sets to do the mapping. You can see the same profile on both the REMA curvature at the top and the ramp image at the bottom, with an example of a ridge line that can be traced from those images. So before I show you the result, I'll just put up the existing model of bed topography from Bed Machine here. One thing to note here is that above the yellow line, that's west of 85 degrees, there's reasonably good topography because that's within the area of the main AGAP survey. Outside of that area, there's a significant drop-off in terms of the resolution of, or the accuracy of the topography that we can resolve using the existing radar data. If I just move on here, I'll show you first the ramp image for the whole area. And then this is actually the whole network of ridges and valleys in the subglacial topography that we think we can see using both data sets, the ramp and the elevation model REMA. And if we compare it to the bed topography, this gives us a very good kind of first order impression that actually there is a lot of good relationship here between what we can see from the surface and what we know already exists from the existing bed model. But also, if I just pointer up here. We can see that in some of these, I know this is quite a busy image, but we can see that in some of these areas, there's actually significant detail that we've been able to see and map from the surface that goes above and beyond what we know from the radar data and the interpolations that have been produced from them. Of course, we also have this area down here where this new map significantly improves on what we knew before. There's definitely confirms that the surrounding areas of the Gambut serves, the foothills are still contain a lot of topographic variation, and there's potential maybe in the future to expand this mapping further. So actually one of the first things to note, and that has been noted previously about this landscape, is the presence of these very long straight valleys that dominate most of the topography, the kind of the layout of the topography in the central Gambut surface. So that is actually still evident in this new data set. But what we can do now that we have kind of a broader picture of the whole landscape is we can look at the distribution of valley and length over the whole area, and we can see that although there are, yes, some extremely long valleys going hundreds of kilometers, that overall the valleys are distributed normally on a logarithmic scale, which is what we would kind of expect from a fluvial network. We can also look at the valley and ridge orientation, and what we find actually is that there's a bias towards a particular orientation, which is running from top left to bottom right in our projection. That equates to roughly northeast to southwest in real terms, and that's actually probably quite heavily swayed by some of these very long valleys there. An interesting point to note is that this is also similar to the orientation of the main ice divide that overlies. And since there is, we know that there is going to be differences in how surface features are expressed depending on what the relation, the difference in angle is between the ice flow going over it and the feature itself. We want to just check whether that's what's causing this impression, and it might not actually be a real trend in the topography. But if we look at the final plots on the right here, we can see that there is a slight increase in the total length of valleys and the total length of ridges that are oriented at right angles to ice flow compared to those that are oriented parallel. But overall, there is a fairly even distribution, which gives us confidence that what we are seeing is actually a pretty comprehensive overview of all of the directional and kind of orientational diversity in the landscape. Another thing we can look at is the width or spacing of valleys on a kind of local to regional scale. Essentially what this gets at is what is the kind of minimum wavelength of topographic variation in any given area. We're talking about valley width here as from one ridgeline to another. So comparing that to the bed topography on the top right here and the valley width as a local mean on the bottom right, we can see that there's quite a close relationship with a greater abundance or more valleys at a narrower spacing at higher elevations. The key thing here is that the local valley width is actually significantly beneath the flight line spacing of the AGAP survey, which was 5 kilometers. And that shows us that there is quite a lot of local topographic variation in this landscape at higher elevations, which is not being picked up by the interpolated DMs created from the radar survey. Okay, so this is the last thing that I'm going to show you today. There is the potential from the data we have to actually start to model the paleo drainage. So if we take our valley lines and use the direction of those lines as an indication of paleo flow, when those valleys were formed, as we assume this is a fluvial landscape, we can actually take those points and interpolate across the whole region what we think the flow direction might have been, and then use that result to begin to model the properties of the flow of the drainage independently of actually any bed digital elevation model. We can compare what we have here, which just shows the flow accumulation downstream, so overall the upstream area of each pixel, which will sort of relate to the discharge we would expect to see in that channel. We can compare it to the bed machine elevation model, and we can see that it does fit quite well the kind of drainage pattern we'd expect to see. We can also compare it to a drainage pattern derived from the bed elevation model and see that it actually compares quite favorably. There's an improvement in terms of the level of detail. This is not a kind of final version of this. There's still some areas where you can see it's not quite well resolving perhaps some of the connectivity we expect to see in the network, but this is kind of a further place we could take this work. So thank you for listening to this presentation. Just by way of conclusion, here's a few of the main findings. So far, this is still kind of work that we're getting on with at the minute. Basically, yeah, we use satellite remote sensing data to map the planform structure of the gamberts of subglacial mountains independently of any other actual elevation data set of the bed. However, those existing bed models do verify what we found, but we can add significant detail to them. A key finding is that there is significant small scale variation in terms of valleys and ridges in upland areas, and that actually could be an important result when it comes to thinking about locations for long-term cold-based ice, because even those small variations in relief can affect whether ice is frozen or melting at the base. Overall, this landscape is one of fluvial origin in terms of the incision of the valleys, and we can also see some details of early local scale glaciation. This is probably one of the earliest regions in Antarctica to have been glaciated. And the final point there, as I was just talking about, we can, using these data, begin to start thinking about the drainage properties of this region without actually knowing what the detailed elevation of the bed topography is. Thank you.
Thanks very much, Edmund. We've got a couple of hands up, so if we can go through these questions reasonably quickly, that'd be great. Mayuri, you've got a question. Do you want to shout it out?
Yes, Edmund, I wanted to ask that you explained about the presence of a paleo drainage in the area in GSL. So could you just give a rough idea of which geological time scale you are referring that this paleo drainage would have been present in that particular specific time frame? So could you just mention which time scale, I mean, in terms
Yes.
of geological time scale, which time period you are talking about?
Okay, so the kind of paleo landscape is in the existing literature is supposed to be perhaps around 200 million years old, I think, since the onset of drainage. That's based on erosion rates from some work by Guy Paxman and others. Then we expect the onset of glaciation to have been about 34 million years ago. So
This
that's
was
the kind of time frame.
This was before any ice sheet formation took place in Antarctica.
That's correct. So the original analysis of the AGAP data and other radar data in this area proposed that this was an ancient fluvial landscape before any onset of glaciation occurred, and that's based on the dendritic valley network that's then been superimposed with imprints of first local scale glaciation, and subsequently it's been buried beneath the ice sheet, and that's over actually a very long time scale in terms of landscape evolution.
Peter, if it's really quick, then ask your question. Thanks.
Okay, I might have to take this offline at Edmund, but nice talk. Very quickly, do you think the fact that you've got several ice divides with zero velocity will affect the amount of detail you can see under there? So, for instance, will that affect your analysis of the fineness of scale of those valleys if you've got zero velocity and very thick ice?
Yes, certainly that's a concern. What you can kind of see on the radar sat image here is that there's the variance in terms of the reflectance values we're seeing is much greater in this area to the left here and up to the top right, which is either side of the ice divide, whereas over where the ice divide is actually much less clear. There's less variation in the surface, the shape of the surface, from which to infer changes in the bed topography. Interestingly, the REMA digital elevation model actually seems to resolve some of that variation beneath the ice divide in greater detail. I don't know exactly why that would be, but certainly overall there's less certainty that we can attribute to the mapping in that area than to other areas.
That's great. Thanks very much, Edmund. We'll move on. If you can unshare your screen, if we can figure out how to do that. And our next speaker is Mayuri Pandey, going to talk about fluvio-glacial signatures from exposed geotechs. So we've been moving all the way up in the landscape of Antarctica throughout this session. So yeah, Mayuri, over to you.
Thank you so much, Jamieson.
Yep, we can see your slides.
Okay. So I will be talking about the fluvio-glacial signatures which we found during the field work in the East Antarctic terrain. So this talk is basically based on the evidences from the sedimentological signatures through the erratics and the moraines which are present in that area. So the broad idea behind this work was that to basically infer the relevance and the significance of the Gambler's Mountain in the present inferred framework of that of Princess Elizabeth Land. We know that what we know from study till date is Gambler's is completely submerged or covered with the ice sheet. One, and then there is a mountain chain which is present. Now, many of the people have related this mountain chain either to the 500 MA age or Pan-African age, or they have also inferred it to be older to the Pan-African age. So the prime idea was to understand the role of Gambler's Mountain in various drifting processes as well as various orogenies which has been inferred in the area. Now, one of the way is the geophysical survey. The other way is to study the offshore sediments and sediments which would have been transported from this campus terrain to the outsourcing of the Prince Bay area, or the PEL terrain, offshore of the PEL terrain. So three major, if you see over here, three major glacial systems, basically the Lambert Glacier, Mellor, and the Fisher, basically transport huge amount of sediments from this terrain to the Brisbane area. Now, from our previous study, we have already inferred the geology of the certain portions of the geology of the Gambusa Mountain. I'm not going into the details of what has already been published, but this gave now addition of recent geophysical surveys and studies have shown that there is, besides this glacial system, we also have a subglacial canyon present in this terrain. Along with the subglacial canyon terrain, recent work which was done by IceTech PELT, have also shown that there is extensive network of subglacial flow which comes from the interior of the PEL terrain to the coastal areas of if you see here, coastal areas of the Brisbane. So considering this flow pattern and the canyon system, we can infer that there will be a possibility, there is a possibility of getting these sediments of this terrain, this completely hidden terrain, to the coastal area. There is a possibility that we may get certain signatures, certain sediment samples, which can help us to infer the geology of this particular area. So with this hypothesis, we carried out the fieldwork in the coastal areas of the PEL terrain. If you see, the fieldwork was oriented towards, it started from the West Pole Hills till the Gilnock Island. The red mark shows the fieldwork which has been carried out in the 41st Indian Scientific Expedition to Antarctica. The areas were decided based on the Google Earth images, which was shown here. So these images show the presence of the moraines, which has been marked in these areas. So based on this identification of the morainal areas, we carried out the fieldwork. The most important areas for getting the moraines were this particular area known as Publication Island, the area close to the Publication Island. And since there was no as such official name to the area, we have named it Moraine Island because it was a huge deposit of moraine present. It has a huge deposit of moraine. Now, interestingly, this particular moraine island has three different types of sediment deposit or the till deposit, morainal deposit. One was the bigger boulders. Second was the outwash plain and with huge amount of tillites. And third was the embedded sediment layers between the two ice sheets. Now, if you see over here, there are bigger boulders which are present, and along with that, there is a small fine-grained material or the sediments which are present over here. So if you see the textural features, most of the grains in the boulders are angular in shape. Okay, I'll tell you the significance of this. If you see here also, they are extremely angular and do not have any significant shape. And if you see the surface of the exposed rock, we see slickened sides, the glacial slickened sides present on the surface of the exposed area in the Moraine Island part. Now, when we talk about the boulders on the ice sheet part, we see that again we are getting huge boulders which are oriented in one direction, but typically are angular in shape. Okay, now these were the boulders. There are certain areas where lots of boulders were exposed, and then there were third type of samples which were collected. Those were the sediment samples which were embedded between the two ice sheets. If you see here, these are the embedded morainal. So these are basically the end morainal type of sediments. All of them are end morainal type of sediments, but from three different settings which has been collected. Now I'll tell you the significance of it. Before that, then we carried out the fieldwork in the West Pole area as well, and we found a similar type of terrain in the West Pole as well. Certain areas of the West Poles were totally devoid of any glacial input, any sedimental input. As you can see over here, we hardly get any of the sediments or any kind of morainal deposit. But if you see here, there is an outwash deposit present, and over here also there is an tillite deposit which is present in the Westfold Hills. Now, this why we are getting such contrasting and the significant distribution of the sediments in Czech. I'll just explain you in the next few slides. When we went to the Rheinbold area, we found that the deposit, the morainal deposit which we are getting, have the grains or the sediments which are, or boulders which are rounded to sub-rounded. Now, this has significance in terms of which type of processes which would have transported these sediments. When we have a rounded to sub-rounded type of texture in the sediments or in the boulders on the rocks, we infer that it is from the fluvio-glacial input. When we, sorry, not the fluvio-glacial, we basically infer that it is from the fluvial input. Only the fluvial input can give you the rounded to sub-rounded type of textures in the sediments. If we are getting this kind of textures, it means there was a fluvial input. However, when we see the Westfold Hill area and when we saw the publication island or the moraine island sediments, we found that this type of input was not, this type of sediment input was not present in those particular areas. Now, there was another type of topography which was present in the area, which was completely devoid of any sediments or moraines or tillites. Now, these were certain areas of landing bluffs, and this particular picture shows the area of Provenance Island. This is the Dalcoy Island, and this particular picture shows the images of landing bluffs. So you can easily infer or usually distinguish between the topography which is present in these, or landscape which is present in these islands, and what I showed you earlier in the Westfold Hills and the Rheinbold area. Now, three different types of sediment deposit, I would say landscapes, were identified during this fieldwork. And if we see the flow patterns which was inferred through the geophysical surveys, and we collectively see which were the islands which were having glacial input, and the islands which were having the fluvial input, and the islands which were totally devoid of any glacial input, we could find that it is directly related to what has been inferred through the ice cap fields, through the geophysical surveys in this area. And they have inferred different flow patterns. If you follow that, then it is easier to explain this differences in the different terrains. For example, this landing block does not have any subglacial flow pattern, and this particular area was totally devoid of any glacial input. And if you see the Westfold Hills, and if you see the Westfold Hills and the adjacent area, there are certain area of the Westfold Hills which have a significant amount of subglacial flow. Rest of the areas are devoid of it. So if we could try, if we could basically track or understand the morainal deposits which were present in the area, we can actually infer directly the subglacial flow. So from this initial or a preliminary study, I infer that whatever the data which was inferred through the geophysical surveys during the ice cap period, we do get certain field signatures, sedimentological signatures, and we find that the data is coherent with the practical geological evidences which we could find on the field. The second thing which is interesting to find out of this work is that the eastern flank of the Mayuri ice shelf shows significantly different type of melting behavior or different type of sediment supply as compared to the coastal areas of the Prince Bay. Why this is happening, it's again entirely a different question, possibly because of the altitude, possibly because of the geomorphological features, or possibly because of the melting, or basically because of the geomorphology. Any other possibility could be there. But the higher melting level could also be significantly observed in the sediment supply in that particular area. And similarly, if you see this area, we do have higher amount of glacial input. So possibly the Prince Bay terrain is not showing significant melting, or not showing the signatures of, at least the signatures of significant melting in the sedimentary rocks or sedimentary input. And what we are in Eastern flag does show certain signatures, sedimentary signatures of fluvial input in that area. So this was the preliminary inferences. We will also be doing the geochemical and mineralogical analysis. We are still waiting for the samples to come, and we are again planning to carry out the fieldwork in 42nd Indian Scientific Expedition to Antarctica, possibly provide more light to what we are inferring presently out of the sedimentological textural features of the glacial and glacial-fluvial input. Thank you so much for the listening to the presentation.
Thanks very much, Mayuri. If anyone has any questions, please type them in the chat, but I'm going to start off just while anyone types. Do we have any idea of the age of deposition, or whether you could get at any of the chronology for the deposition of those fluvioglacial boulders? Is it an LGM deglaciation signal that you're seeing, or is it something different?
Okay, no, we do not have, presently we do not have the idea of what would have been the age of the deposition, but I can say from the exposed and unaltered terrain, it would have been a recent deposit, not very old. But if we follow the flow patterns, we are, which is presently inferred from recent studies, then for sure I can say that there must be some amount of sediment input from the Gambutsa mountains or some nearby areas of the Gambutsa mountains. So possibly we will be able to infer certain geology of the interior of the Princess Elizabeth Land. And
yeah, and of course you need water, and so that, I guess that's the other question, is when was the last enough water flushing to the surface to sort of bring that stuff out where it is. Okay. Yeah, well, that'd be an interesting question to discuss with the heat flow people and the modeling people. But thank you very much. Thanks. If you can unshare your screen, we'll move on to the final talk of our session, and that's Rashmi Gupta. He's going to talk about continuing that sort of movement from onshore to offshore, look at the provenance and tectonic setting of offshore sediments from East Antarctica, and in particular looking at Wilkes Land and Prids Bay. So Rashmi, if you're able to share your screen, that would be excellent. And make sure you unmute as well. We can see your slides, but we can't hear you. So can you unmute?
Okay, a very good evening to all the dignitaries. I'm Rashmi Gupta. I'm going to discuss the evolution of geochemical sediments from the offshore of East Antarctica, from the Wilkes Land area and Prids Bay. So this is the map of Antarctica showing the present day drainage pattern, and this is the Prids Bay area and this is the Wilkes Land, and these black dashed lines mark the ice divide, and they are forming one drainage basin in Prids Bay area and another drainage basin in Wilkes Land area. And these green to blue color lines are indicating the direction of ice flow from the interior of Antarctica towards the coastal regions. And in both the regions, we can see that the movement of ice is similar, and they both are high mass wasting regions. And when glacier move over the bedrock, they erode the bedrock and transport and deposit them in coastal areas. So both the areas, Prids Bay and Wilkes Land, are receiving sediments from the interior of Antarctica. And we already have worked on heavy mineral and rock fragments of the sediments from the Prids Bay and Wilkes Land, and we found a low-grade metamorphic rock of 700 to 800 million year age from Prids Bay, and a similar low-grade metamorphic rock of about 800 million year age from the Wilkes Land. So in the present work, we are comparing the geochemical data of both the sediments from Prids Bay and Wilkes Land, and to see if we are getting similar type of provenance of these sediments, or a similar type of rock is present in the interior of Antarctica, which is the source of sediments in both the regions, Prids Bay and Wilkes Land. So our work is based on the sediments recovered from ODP Expedition 119 in Prids Bay and IODP Expedition 318 in Wilkes Land area. And this map is showing the location of sites in Prids Bay, and these red dots are the location of sites. This is the site 740. 3 sites were drilled in Prids Bay during the expedition. This is the site 740, 742, and 739. 740 is most proximal site, and these 2 sites are distal sites. And similarly, in Wilkes Land area, this red star is showing the location of site in Wilkes Land. The sediments from the Wilkes Land, the age of sediments from the Wilkes Land area is Miocene, and the age of the sediments from Prids Bay is from late Oligocene to recent. So sediments from both the regions are from post Antarctic Ice Sheet formation. So the geochemical signatures will give more accurate information about the sub-ice geology of these 2 regions. So we process the sediments from both the regions for measure and trace elements analysis. And in this diagram, we are plotting the measure elements of site of both the sites in AC/NK diagrams. These blue color dots are from Wilkes Land sediments, and these sky blue color dots are from 740 of Prids Bay, and yellow color symbol represent the site 739 from Prids Bay, and this green color symbol is from 742 from Prids Bay. So chemical index of alteration values from both the areas are average values is 53 for Wilkes Land and 61 for Prids Bay. That means they are showing the similar kind of weathering condition and in both the regions. And in these diagrams, we can also see that the pattern is more or less similar for Wilkes Land and Prids Bay sediments. So they may belong to the similar kind, they may represent the similar kind of provenance in both the regions. So here is the trace element diagram, and sediments from both the regions are representing composition between andesite to granite. That means intermediate to felsic composition. And zirconium and hafnium value of sediments from both the regions are low. That means sediments from both the regions are not recycled, and they are representing the primary provenance, and they are directly derived from the rock that is like within the interior of Wilkes Land and the Prids Bay in Princess Elizabeth Land. And in this diagram, we are getting more mafic or basic signatures from the site 740 than Wilkes Land sediments, which is in contrast with what we should expect, because Wilkes Land have a ferrar large igneous provenance in the interior, and we should get more mafic signature from sediments of the Wilkes Land. So there could be 2 possible reasons. The first reason is the extent of ferrar large igneous provenance inferred from the geophysical surveys is not up to the coastal areas, but a little bit in the interior of Wilkes Land. And our another set of work from mineralogical attributes, we have all concluded that extent of ferrar large igneous provenance as inferred from geophysical surveys is not completely true, and it is little more complex. And the why site 740 sediments are showing more mafic signatures, that could be because of we are getting in this diagram, we can see that we are getting direct supply from Westfold Hills to the site 740, and that is the reason, because of that could be the reason because of we are getting more mafic signatures in site 740 than Wilkes Land sediments. And this is the diagram of, this is a normalized coordinate normalized plot of both the regions. And felsic rocks usually contain low, higher LRE by HRE values and negative europium anomaly. In both these areas, we are getting negative europium anomaly and 4 to 9 LRE versus by HRE ratio, and 7 to 10 for Wilkes Land. That means they both represent the intermediate to felsic provenance, and we are getting certain high RE values for Prids Bay sediments That may be because of we are getting more monazite and zircon in the sediments of Prids Bay. And from this discussion, I can conclude that the sediments from both the regions are not recycled and indicate the primary provenance. And the extent of ferrarlargic igneous provenance in the Wilkes land is not extended to the coastal areas, but a little bit in the interior of Wilkes land. And the sediments from both the regions are showing similar kind of provenance, that means felsic to intermediate kind of rocks are present in the interior. And the reported ages of 700 to 800 million years from low-grade metamorphic rocks from Prids Bay and Wilkes land could be from a similar or in continuation of orogeny present in the interior of East Antarctica. Thank you.
Thank you very much. If anyone has any questions, again, please type them in the chat. While we do that, I'll abuse my position as chair and ask or just check, were these samples taken from the top of the cores? Are they representing the material that's coming out at modern time? Sorry, did you understand the question? So yeah, is the material from the top of the cores, or what age is the material? Do you know?
Sorry, can you repeat the question?
What age is the samples that you're analyzing? Are they from core tops, or are they throughout the core? What are they?
Actually, sir, the sediments from my Wilkes land area of Miocene age, throughout the core is Miocene age, and the sediments from Prids Bay is ranging in age from Oligocene at the bottom, from site 739, and more recent Pliocene, from more recent Holocene to Pleistocene from the 740 and 742.
Okay, and so you don't see big changes in provenance through time in these records?
Sorry, sir?
Do you see any change in provenance from the bottom of the cores to the top of the cores?
Actually, sir, we are not significantly getting from bottom to top. We are getting almost similar kind of. Here we can see that all the sediments from top to bottom are showing almost similar kind of trend, similar signatures.
Yeah. Okay, so that's interesting, because it maybe means that the flow pattern of the ice sheet hasn't changed too much over that time, and the material it's picking up, or the place it's been picking up material, hasn't changed too much over time. So thank you for that. Excellent. If you can unshare your screen.
Yes.
Thank you. So thank you to all our presenters. We've got a few minutes before I think Sophie Nowicki is going to be doing a keynote. So I thought I'd give the opportunity to our poster presenters if they wanted to briefly mention anything of interest about their posters. And we've only got a couple of posters in the session. So Anya, did you want to say something? And Rashmi, if you can unshare, that's perfect. Yeah, hi Anya.
Hi, Stewart. Good evening, everyone, as it is here. So hopefully there's a poster sort of visible there.
We can see it, yes.
Great. Zoom bingo. Yeah, so just to share some good news, really, rather than some scientific results. We're all terrifically interested about this intriguing layer between the sort of deeper earth and the ice sheet above. And we've been fortunate in the Australian program to have myself and Kate Selway and Mackie gained some funding to sort of establish a new instrument facility, which goes under the name of GRIT, Geophysical Research Infrastructure for Antarctica. And both Kate, whose expertise is in magnetotellurics, and myself, I'm mostly in terms of seismology, we're interested in both deep targets and in this sort of intriguing ice bedrock interface zone as targets. So yeah, just to share that we have a sort of a pilot deployment out right now, sort of along some traverse lines from Casey Station. That's the middle map there. And Kate's just back from a major deployment in Greenland, looking at using those instruments to make some constraints on the geoelectric structure of the deep lithosphere there for isostatic adjustment connections. So yeah, we are looking to quite a major season, not this coming Antarctic season, but in 2023-24, possibly in the Denman Glacier region, and that's going to be sort of some shallow targets there on the ice bedrock interface. And yeah, beyond 2024, I'm certainly interested in some collaborative discussions. So yeah, there's my email address just in the corner there, if anyone wants to make contact with myself or Kate or Matt. Thank you, Stuart.
Thanks, Anya. Do you have an indication of, you're talking about this being sort of infrastructure. How long do you anticipate it might be able to be in place?
So the idea, in Australia, we have a situation, as you probably know, where it's a very big deal to cross the Southern Ocean, a much bigger hop than from the Falkland Islands to the peninsula and further south. So the idea of this facility is that the instruments are based in Antarctica, so we don't waste a season shipping them. That means they can be sort of uplifted and moved to a new location. And also, yeah, we don't have to compete with sort of Australian projects in terms of moving them to a new location. Yeah. And yeah, worth noting that we're really interested in early career researchers in terms of their ideas and starting to roll out to yeah, a greater user base of researchers.
Excellent. Thank you for sharing that with us. And if you can unshare your screen.
Sure.
And we'll see if Ian wants to say, and I think you've got a couple of posters, haven't you, Ian?
I think that might be Anya instead. I only have.
Okay.
I'm not sure if Anya wanted to go again or.
Oh, to be honest, I don't have the other one handy. So if anyone's picked up on that that topic, feel free to email me.
Thanks. So Ian, yeah.
Sure. Yeah, I can share my screen as well. Awesome. Yeah. So hopefully you can see that. Should be good.
Yep, we can.
Awesome. Well, thanks, Stuart. Yeah, so hi, everyone. And apologies if I sound or appear a bit tired. It's a bit late over here. So yeah, myself, Anya, Tobias, and collaborating with some people across the globe, really, have been trying to develop a toolkit, a kind of a guidebook for yourselves and for the wider geoscientific community, how we should use geophysical methods to understand and interpret the targets that we're interested in, ranging from the crust all the way up to the ice surface. And so this poster kind of is like a subsection of that review publication, which is hopefully going to be submitted within this year and next few months. So the idea is to break down methods like the passive seismic methods into comprehensible ideas that, for someone who is unfamiliar to the methods or someone who is interested in applying sort of multivariate campaigns within their future plans, understanding how they could incorporate methods like the passive seismic methods, which are very useful in terms of their sort of remote deployments and monitoring temporal changes in the subsurface, how you could use that to better constrain the targets you want to understand. So in this case, just looking at the passive seismic methods, kind of showing the main 4 methods I consider that we currently use in Antarctica and in the Arctic. And yeah, just no real results, but just trying to hopefully guide people towards the right direction. And there'll hopefully be more to come within the review publication that's going to kind of cover a broad scope of seismic, electrical, electromagnetic, and sort of airborne potential field surveying. So yeah, if you have any questions or any ideas, always happy to listen. You can find my email tucked away in the corner, the top left corner there. So yeah, thanks, Stewart.
Thanks, Ian. Nice to see some productive PhD work happening since we last spoke. Yeah, if anyone has any questions, then pop them in the chat. I'm just going to check. Oh, Anya, Pippa has asked a question. And she says, great to see this new activity. Are the measurements time limited, or have you secured permission or funding for longer term measurements? I guess that's sort of what I was asking, but yeah, it's that long-term question. I know Pippa's struggling with that at the moment.
Oh, well, we're full of optimism, of course. I mean, I think we feel like we've sort of cracked our greatest limitation in terms of having a facility located in Antarctica, and there's I'm involved with a kind of strategic planning initiative for geophysical mapping coming out of Australian Antarctic Division. So there's definitely high hopes that there'll be a kind of continuous rolling data collection. Just the question of exactly can we get to those really remote locations that we love to get to is probably still an open question.
That's effectively going to have to be funded by individual grants going to tackle individual questions. Well,
no, we hope that there will be, or many of us are involved in a quite a collective, or there's 2 collective funding initiatives essentially in Australia at the moment. I'll spare you the acronyms, but yeah, definitely more leaning towards coordinated initiatives with multiple researchers rather than individual groups going alone these days. Yep. So yeah, that's exciting.
Good, excellent. Well, I think that brings us to a nice point to close ahead of the next session starting. So I just wanted to say thank you very much to everyone who's turned up. Thank you very much to everyone who has taken the time to present. Please make sure we go and look at the posters that are part of the sort of more general poster session. And I think the key thing is to to follow up discussions. It's really difficult in these online conferences. We're in a compressed time and we can't now go for a cup of coffee or a beer and chat about it. So please follow up with people that you've heard today and talk to them about their work and think about what their work might mean sort of in the broader context of, I guess, understanding East Antarctic ice sheet behavior and how this sort of geological side of things and topographic side of things might feed into that sort of broader question. So thanks very much for coming, and I guess we'll see you at some point in due course, maybe next year. Thanks.
Thank you, Stu.